A black hole does not pull you in like a monster from fiction. It bends the very shape of time itself. Even now, as you breathe in this moment, somewhere in the distant dark, space-time is folding quietly around an object so dense that seconds and centuries slip into different rhythms. Near its edge, time stretches thin. Far from it, time flows freely. And in this gentle difference, a strange truth emerges. Black holes are not just places where light disappears. They are places where time changes its meaning. Settle in. Let your breath slow. Tonight, we'll drift into the silent mathematics of gravity, into the unseen engines at the centers of galaxies, into the physics of horizons and the reasons time itself can run at different speeds. Not as a threat, but as a reminder of how vast and calm the universe truly is. If this quiet journey brings you even a moment of rest, I'm deeply grateful you're here. A gentle like or a soft tap on subscribe helps keep these calm explorations alive, and your presence here means more than you know. Now we drift into part 1. Part 1. What makes a black hole? A hole in the first place. A black hole begins not as an empty space, but as a star that has run out of options. When a massive star collapses under its own weight, gravity overwhelms every force that once held its atoms apart. What remains is a region where space curves so steeply inward that nothing, not even light, can climb back out. It is not a hole in the sense of absence, but in the sense of inevitability, a place where paths only go one way. To understand this strange destiny, imagine a star many times larger than our sun, a brilliant sphere of hydrogen and helium burning so intensely that its outward light pressure holds gravity at bay. For millions of years, that balance remains stable. Gravity pulls inward, fusion pushes outward, and in that quiet tug of war, the star lives. This is the secret heartbeat of every shining point in the night sky, a perfect equilibrium between collapse and light, but eventually the fuel runs thin. The fusion weakens, and gravity, patient and persistent, begins to win. For a star above a certain mass threshold, this victory is absolute. The core implodes at incredible speed, crushing atoms, then nuclei, then the very distinctions between matter itself. Electrons are forced into protons, creating neutrons. Neutrons are forced into forms we barely have language for. What remains is a core so dense that a teaspoon would outweigh mountains. And for the most massive stars, those perhaps 20, 30, or even 100 times the mass of the Sun, this collapse continues past every frontier our physics can tolerate. A point of no return is formed. The star does not explode outward. It folds inward, dragging space-time behind it. The result is a black hole. But the name black hole often misleads us. We imagine a void, an empty pit, a nothingness swallowing everything. The truth is subtler, quieter, and far more beautiful. A black hole is not empty. It is a region of space where gravity curves pathways so dramatically that all motion, all light, all particles, all signals flows inward toward the center. In normal space, you can turn around, choose another direction, retrace your steps. Near a black hole, that freedom fades. Space itself leans inward, like a slope so steep no traveler can climb back up. This inward leaning is what we truly mean by a hole. But how does gravity bend space? How does mass shape time? According to Einstein's general relativity, gravity is not a pulling force. It is the curvature of the fabric of space-time. Imagine placing a heavy object on a trampoline. The surface dips. Now imagine rolling a marble across that surface. It naturally moves toward the dip. The marble is not being pulled. It is simply following the shape of the fabric beneath it. In our universe, mass shapes space-time the same way. A star creates a gentle well. A planet creates a smaller one. But a black hole is a well so deep and steep that the edges nearly fall vertical. Once you pass the boundary, the event horizon, every possible path points inward. This horizon is the part of a black hole most people misunderstand. It is not a surface. It is not a shell. It has no texture, no material. It is a boundary created by the flow of time itself. Outside the horizon, you can still escape if you move fast enough. Inside, escape becomes mathematically impossible, not because you are trapped in a cage of matter, but because time itself changes orientation. The direction we normally experience as forward in time now points inward toward the black hole's center. This is the deepest truth. Inside the event horizon, falling inward is not a choice. It is the passage of time. But from far away, the story looks different. To a distant observer, objects falling toward a black hole appear to slow down. Their signals stretch. Their clocks seem to tick more slowly. They fade into red, then into darkness. From our perspective, they never truly cross the horizon. They simply approach it and freeze. But to the falling object itself, nothing strange happens at all. The crossing is silent, smooth, unremarkable. A moment like any other, except that every possible moment afterward leads deeper. This difference between perspectives is not a trick. It is the nature of time in curved spacetime. Both viewpoints are true within their own frames of reference. Reality is wider than a single perspective. So if the horizon is a boundary of time, what lies inside? At the center of a black hole is what we call the singularity, a point where our equations of physics break down. Not because it is mysterious in a metaphysical sense, but because the densities and curvatures involved exceed what general relativity can describe. A singularity is not a physical object. It is a signal that our theories have reached their limits. It marks the place where quantum gravity must take over, where spacetime becomes quantized, turbulent, and strange. We do not yet understand the singularity. It is the most mathematically guarded secret in all of astrophysics. But we do understand the horizon. And that's enough to explore the heart of the question. Why is a black hole a hole? Because gravity shapes not just space, but the flow of time. Because the inward path is not optional, it is woven into the geometry of spacetime. Because once mass collapses past a certain threshold, the curvature cannot be undone. Even Hawking radiation, which slowly evaporates black holes over unimaginable spans of time, does not reverse the collapse. The hole remains a one-way journey for anything that enters it. At its core, a black hole is an endpoint of matter, motion, and time. But perhaps the most astonishing truth is this. Black holes are not rare accidents. They are fundamental to the architecture of the universe. Nearly every large galaxy orbits a supermassive black hole at its center. These giants, millions to billions of times the mass of the Sun, anchor the structure of galaxies. They regulate star formation. They shape the flow of gas, dust, and dark matter. Without them, the cosmos would not look the way it does. Far from being destructive anomalies, black holes are organizers of the universe. Their gravity sculpts galaxies into spirals. Their jets seed space with energy. Their accretion disks shine with light so bright it can be seen across billions of light years. And quietly, at the center of each one, the same truth remains. A place where time leans inward. Even the name we've given them, black hole, may be too small for what they represent. They are wells in spacetime, fountains of energy, engines of galaxies, and laboratories of intense physics. They are the places where our understanding stops, but our curiosity continues. They are points where the universe folds its fabric so tightly that it creates a doorway of sorts, a threshold where our current laws of nature reach their limit. So what makes a black hole a hole? It is gravity's final answer. A curve so deep that all paths converge, a place where time itself flows in only one direction, a region where matter no longer behaves like matter and where the universe writes its most extreme chapter. And as we drift deeper into this quiet exploration, one question naturally follows. If this is what happens when a star collapses, what happens to time itself as we approach the horizon? Part 2. Why does time slow down near a black hole? According to general relativity, gravity is not a force but a curvature of spacetime. The stronger the curvature, the slower time flows. Near a black hole, the warping becomes extreme. A clock falling toward the horizon ticks more slowly than a clock far away. To the distant observer, it almost freezes. To the falling observer, time feels normal. This quiet mismatch is one of the universe's most haunting illusions. To understand why time behaves this way, imagine space-time as a fabric stretched gently across the universe. In most places, this fabric bends only slightly. You move through time at your usual pace. A second feels like a second. A minute feels like a minute. The physics is calm, predictable, almost flat. But near a massive object, this fabric begins to sag. The deeper the sag, the more time tilts toward the mass. If space curves downward, then time, woven into that same fabric, bends with it. The concept is strange, but beautifully simple. What we experience as slowing time is just the geometry of space-time guiding the rhythm of moments. Einstein showed that mass and energy shape space-time, and space-time tells everything, light, particles, even time itself, how to move. So when a black hole forms from a collapsing star, the curvature becomes so severe that the normal flow of time begins to change. Not abruptly, not suddenly, but gradually, smoothly, silently. Imagine two clocks. One remains far from the black hole, floating in the gentle curvature of space. The other drifts downward toward the horizon. Both tick in perfect rhythm when they begin. Both are built the same. Both are free of any mechanical irregularity. Yet, as the second clock sinks deeper into the curved region, its ticks begin to slow, not because the clock is malfunctioning, but because the flow of time around it has changed. From your vantage point far away, that lower clock seems to drift into slow motion. Its seconds stretch, its signals weaken and redden as the wavelengths of its light lengthen. If it continues downward, the clock appears to nearly stop as it approaches the horizon. For you, watching from afar, it will never fully cross. But for the clock itself, or for the person holding it, nothing unusual happens. Their heartbeat remains steady. Their breath flows naturally. Their seconds pass at the same familiar pace. Time feels normal because each observer always experiences their own proper time, measured by their own path through space-time. This is the quiet tension at the heart of relativity. Both perspectives are correct. Now, imagine standing at a safe distance from a black hole. You drop a small object, a probe equipped with a pulsating light beacon. Each pulse marks a second. As it falls, you count the flashes. One by one, they slow. 1 second becomes 2. 2 become 3. The signal grows dim and stretched. Eventually, the pulses fade until they seem to stop completely. The probe hovers at the horizon, frozen forever in your field of view. But the probe's onboard clock tells a different story. It has crossed the horizon long ago. This discrepancy is not an illusion of vision. It is a consequence of space-time curvature. For the distant observer, the horizon is an asymptote, something that can be approached but never reached. For the falling observer, it is just a point in space they pass without any violent change. The horizon is not physically hard. It is the boundary between different futures. To understand why time stretches this way, we must look at the mathematics of gravity. In general relativity, the rate at which time passes depends on the gravitational potential. The deeper you are in a gravitational well, the slower your clock runs relative to someone higher up. You already experience this on Earth. A clock on a mountain ticks slightly faster than a clock at sea level. The difference is tiny, nanoseconds per day, but measurable by atomic clocks. Now imagine the same principle amplified by millions of times. As you descend toward a black hole, you fall deeper and deeper into a gravitational well so steep that time changes dramatically. A few meters can mean years of discrepancy compared to someone far away. The closer you get, the more pronounced the effect. At the horizon, for any distant observer, the discrepancy becomes infinite. Time appears to stop. This behavior is known as gravitational time dilation, and it is not merely theoretical. We rely on it every day. GPS satellites orbit high above Earth where gravity is slightly weaker. Their clocks run faster by tens of microseconds per day. Engineers must correct for this using Einstein's equations, otherwise your phone's navigation would drift by kilometers. Gravitational time dilation is real. it is measurable. And near a black hole, it becomes absolute. But to truly grasp this phenomenon, imagine not just clocks, but lives. Suppose two travelers journey together near a black hole. One remains in a region of gentle gravity, circling safely at a distance. The other ventures closer to the horizon. When they return to meet again, the explorer who approached the black hole will have aged less. Days for one may have been years for the other. Their timelines no longer match, not because anything was broken, but because their paths through spacetime differed. This effect, the stretching of time by gravity, is the closest thing nature has to a real time machine. Yet, in the midst of this extreme physics, something remains profoundly elegant. Time dilation is smooth. There is no tearing, no ripping, no sudden shift. It feels as calm as gravity itself. But why does the distant observer see the infalling clock freeze at the horizon? Why does the falling observer feel nothing special while crossing? The answer lies in the structure of spacetime. The horizon marks the place where the inward pull of gravity becomes so strong that even light cannot escape. For an outside observer, signals from the falling object must climb out of an increasingly steep curvature. The climb stretches the signals and slows them. Eventually, the signals redshift into wavelengths too long to detect. The last thing you ever see from the falling clock is a dim, stretched flash of light. Then, nothing. But the falling observer remains unaware of this silence. Their time flows normally. They pass through the horizon without noticing. Because locally, physics behaves just as it always does. The horizon is dangerous only globally, not locally. It is a boundary of destiny, not of sensation. In this way, black holes reveal a deeper truth about the cosmos. Time is not universal. There is no single clock that measures the same rhythm for all observers. Each object moves through its own timeline, shaped by energy, velocity, and gravity. Near a black hole, these differences are magnified into breathtaking extremes. Seconds and centuries can coexist, separated only by a few kilometers of curved spacetime. And so, when we say that time slows near a black hole, we are saying something more profound than it seems. We are saying that time itself is pliable, that the universe allows moments to stretch and bend, that the very rhythm of existence is not fixed, but responsive to matter and energy. As we drift deeper into this calm exploration, one question naturally follows. If time can slow so dramatically near a black hole, what happens to space itself as we approach the horizon? Part 3. What happens at the event horizon? The event horizon is not a physical surface, it is a boundary in time. Once crossed, every possible path leads inward, never outward. Light that tries to escape curves back, as if time itself leans toward the center. To an outside observer, nothing truly passes this boundary, it simply fades, slowing into darkness. To the object falling in, the crossing is silent, smooth, unremarkable, just another moment. To understand this strange boundary, imagine floating toward a black hole with no fear and no resistance. Space around you remains calm. The stars behind you still shine. Nothing distorts your vision in any dramatic way. Your ship doesn't shake. Your heartbeat doesn't quicken. The event horizon, from your point of view, has no texture and no warning. It is simply a location in spacetime where the rules of your future quietly change. This is the most important truth. The event horizon does not mark a physical barrier. It marks a shift in what is possible. Outside the horizon, you can still escape if you exert enough force. Inside the horizon, escape becomes impossible, not because of walls or pressure, but because the geometry of spacetime has tilted so deeply that all paths point inward. Forward in time becomes inward in space. To grasp this, imagine time as an arrow. Far from a black hole, the arrow points upward, forward, outward, into the future you expect. But as you drift toward the horizon, the arrow begins to rotate, it leans, it tilts, and at the horizon itself, the arrow has turned fully inward. From that point on, falling deeper is not a choice. It is what forward in time means. Your motion is no longer governed by preference. It is governed by geometry. This redefinition is what makes the horizon so profound. In ordinary space, you can choose to move in any direction. Near a black hole, time itself picks the direction for you. But this transformation is invisible to you as you cross. Locally, everything feels normal. The horizon does not glow or ripple. There is no sudden spike in gravity, no violent pull, no sense of falling into danger. According to general relativity, the only way you would know you've crossed the horizon is by looking out at the universe behind you and noticing that the outside world is receding into silence. But even that realization comes gently. Now imagine someone watching you from a safe distance. To them, your approach to the horizon looks different, strange, distorted, incomplete. As you near the boundary, your signals stretch, your light redshifts, your physical motion slows. Each moment they see from you is delayed more and more. What is a heartbeat for you becomes a slow pulse for them. What is a second for you becomes minutes, then hours, then centuries for them. From their viewpoint, you never quite reach the horizon. You fade, you dim, you freeze. The last photons you send outward crawl through warped spacetime. They struggle to climb out of the steep gravitational well. Their wavelengths stretch until they slip into infrared, then into microwaves, then into frequencies that no instrument can detect. Eventually, all evidence of you disappears. To the outside world, you are a ghost suspended at the boundary, never falling in. But the truth is that you crossed long ago. This discrepancy, this quiet disagreement between observers, is not a paradox. It is a consequence of gravity's effect on time. The event horizon is therefore two things at once: a never-reached boundary for the distant observer, a perfectly crossable moment for the falling observer. Both descriptions are true because each observer is bound to their own timeline. In general relativity, reality looks different depending on your motion and your position in the gravitational field. There is no single universal story that includes both perspectives without contradiction. Instead, the perspectives coexist, each internally consistent. This is one of the most hauntingly beautiful aspects of black holes. They break our human expectation that time should be the same for everyone. But the horizon is more than a temporal boundary. It is a one-way membrane, not made of matter, but of geometry. Anything that crosses its threshold continues inward toward the singularity. Not because of force, but because nothing else is mathematically allowed. If we want to visualize what this inward pull feels like, we must consider tidal forces. Even large black holes, the supermassive kind found at the centers of galaxies, have tidal differences across the human body so small you might not notice them. You could float through the horizon of such a giant without discomfort. But in smaller black holes, those a few times the mass of the sun, the difference in gravitational pull between your head and your feet becomes enormous. You would be stretched, elongated, and ultimately torn apart. This spaghettification does not happen at the horizon itself. It happens closer to the center, where the curvature increases even more sharply. So the horizon is not where danger necessarily begins. It is where destiny becomes fixed. Inside the horizon, your future is directed inward. You cannot choose otherwise. Even beams of light, the fastest travelers in the universe, must follow this rule. They spiral inward, bending along the deepest curvature of spacetime. No signal escapes, no information leaves. Everything that crosses is sealed from the outside universe. This is why black holes appear dark, not because they absorb light like a pigment or material, but because light within them is trapped by time. Now, you might wonder, if nothing escapes, how can we ever detect a black hole? The answer lies in what happens outside the horizon. Matter falling toward the boundary often forms a glowing accretion disk, a swirling, luminous ring of gas heated to extraordinary temperatures. Friction and magnetic fields cause this gas to radiate X-rays, visible light, even gamma rays. Black holes can therefore appear as bright as entire galaxies, lit by their surroundings, not by their interiors. The event horizon. Telescope's image of the black hole in galaxy M87 is not a photograph of the horizon itself, but a picture of the shadow cast by the horizon against the glowing disk of gas around it. The bright ring is the last orbit where light can circle without falling in. The darkness in the center is the region where light cannot escape. What we see is the outline of inevitability. This brings us to something even stranger. The horizon is not a fixed surface. It changes shape. It grows as the black hole gains mass. It can ripple like water when black holes collide, producing gravitational waves that stretch and compress spacetime across the cosmos. When two black holes merge, their horizons blend into one larger horizon almost instantly, a silent, elegant fusion dictated by relativity. Even after merging, the new horizon rings like a struck bell. These oscillations fade quickly, radiating energy outward in the form of gravitational waves. Detectors on Earth, like LIGO and Virgo, have recorded these faint tremors from billions of years ago. They are the after-echoes of horizons reshaping themselves in the deep, dark past. This is why the event horizon matters. It is not a place, but a law, a boundary written into space-time, a threshold across which the universe behaves differently. And yet, for all its severity and finality, the crossing itself is gentle. The horizon does not roar. It does not resist you. It does not signal danger. It simply marks the moment your future becomes inward. And as we drift deeper into this quiet story, one question lingers softly in the background. If the horizon is only a boundary in time, what lies beyond it, and how does space-time behave on the journey inward? Part 4. Do black holes really stretch objects like spaghetti? The tidal forces near a black hole can differ dramatically between your head and your feet. For small black holes, this difference becomes so intense that matter is stretched into thin streams, a process astrophysicists call spaghettification. But around supermassive black holes, the gradient is gentle. You could cross the horizon without feeling a thing, not because the danger isn't real, but because gravity changes slowly over vast distances. To understand why this stretching happens at all, imagine gravity not as a single downward pull, but as a gradient, a difference in force between two nearby points. On Earth, tidal forces are the reason the oceans rise and fall twice each day. The moon pulls more strongly on the side of Earth facing it than on the far side. This slight difference stretches our oceans into two bulges, and our planet rotates beneath them, creating tides. Now, imagine this same phenomenon taken to an extreme. Near a black hole, gravitational tides can become powerful enough to tear apart stars, planets, and even the atomic structure of matter itself. But the key is not the black hole's total mass, it's the steepness of its gravitational curve. The smaller the black hole, the steeper the curvature near its horizon. The steeper the curvature, the larger the difference in gravity between your head and your feet. And the larger that difference, the stronger the tidal stretching. In a small stellar mass black hole, something perhaps 10 or 20 times the mass of the Sun, the tides near the horizon are incredibly steep. A human body approaching such a black hole would feel the front being pulled much harder than the back. The difference grows exponentially with each step closer. Eventually, you are stretched into a long, thin filament. This is not poetic exaggeration. It is the literal behavior predicted by general relativity. Matter becomes a thread, an elongated stream falling deeper and deeper into curvature. But with supermassive black holes, those millions or billions of times the mass of the Sun, the horizon is far from the core. Gravity still grows stronger as you descend, but it does so gradually. The curvature is gentle. If you floated past the horizon of a supermassive black hole, you would not feel stretched or torn. At that scale, the tidal difference between your head and your feet could be insignificant, perhaps smaller than the tidal difference you feel on Earth during the rise of the ocean. It is not the black hole that is different. It is the distance between the horizon and the central singularity. In a small black hole, the singularity is close to the horizon. In a supermassive one, the singularity is far deeper inside. The curvature increases more gradually, giving you more room where everything feels deceptively ordinary. This is one of the quiet ironies of astrophysics. You are far safer crossing the horizon of a monster than the mouth of a small one. But tidal forces do not simply stretch objects. They shape the behavior of matter on cosmic scales. Consider a star approaching a black hole. If the star drifts too close, the difference in gravity between its near side and far side becomes overwhelming. The star elongates, it distorts. It is pulled apart into long ribbons of plasma. These ribbons loop around the black hole, spiraling inward and forming luminous streams that heat up as they collide with themselves. This is the violent cousin of spaghettification, the tidal disruption event. When such events occur, astronomers observe bright flares, bursts of radiation that can outshine entire galaxies for a brief moment. These are the signatures of matter being torn into filaments, stretched thin by the gradient of spacetime. But the stretching does not end with stars. Even planets are vulnerable. If a world like Earth wandered near a stellar mass black hole, its rocky interior would not hold together. The difference in gravity between its core and its crust would rip it apart. Oceans would be drawn upward, mountains would fracture, the entire planet would dissolve into a thin orbiting stream of dust, rock, and molten debris. Yet to a distant observer, this destruction would appear strangely slow. The falling matter would approach the horizon, stretch, warm, and glow, then fade. It would seem to freeze at the edge. But inside the frame of that matter, the fall is swift. The stretching is sudden, the transformation is absolute. The universe allows both truths at once. Even light itself is stretched. Photons climbing out from the stretched matter lose energy, growing redder and redder until they disappear. This redshift is another expression of the same tidal gradient. Not only does space stretch matter, it stretches the very signals matter sends. But the strangest consequence of tidal forces is their role in the interior of a black hole. The increase in curvature as you fall inward becomes so extreme that eventually the difference in gravity across your own body grows infinite. The closer you get to the singularity, the more time and space distort. Time points inward, space compresses along other directions. You become a filament aligned with the flow of space-time itself. This is why spaghettification is not a violent tearing in the conventional sense. It is a reorientation. Your body aligns with the direction gravitational curvature demands. You do not snap like a rope. You are drawn into the geometry. You follow the shape space-time sets for you. Even atoms cannot resist this. Electrons are pulled from nuclei. Nuclei are pulled from each other. Eventually, even quarks, normally confined inside protons and neutrons, are drawn apart as space-time curvature overwhelms the forces that bind matter together. Not because gravity is inherently stronger, but because the tidal difference across each particle becomes greater than the forces holding those particles in place. At the singularity, all distinctions vanish. Every direction leads inward. Space-time collapses. The familiar fabric of geometry dissolves. This is the point where physics as we know it ends. Not because something magical occurs, but because our equations no longer describe what space-time becomes under infinite curvature. In this sense, spaghettification is not an oddity of black holes. It is a symptom of the deeper truth. Gravity is geometry, and geometry shapes everything that enters the well. But we must return to the contrast between small and large black holes. The stretching effect is not a universal experience at the horizon. For a supermassive black hole, you can cross the horizon safely and only feel the spaghettification much later, deeper within. You would drift inward, unbothered, floating peacefully through space-time. The stars behind you fade. The universe outside quiets. Locally, nothing announces the danger. This paradox, gentle crossing, inevitable stretching, remains one of the most quietly unsettling aspects of black hole physics. The danger is real, but delayed. It waits, it deepens, it arrives only when the curvature demands it. If we could watch matter fall into a supermassive black hole from afar, the last thing we would see is the stretching of its light, not its body. It would glow briefly as tidal forces heat it. Then, its signals would redshift into darkness. The stretching of matter is a story seen from the inside, not from the outside. And so the image of spaghettification, the long, thin strand of matter falling inward, is only half the truth. The other half is quieter, the slow, smooth descent before the gradient grows too steep. This opens the way to a deeper question. one that follows naturally as we continue drifting into the geometry of black holes. If stretching is only the beginning, what lies at the very center where space and time collapse completely? Part 5. Why are black holes the universe's most efficient engines? Nothing in the universe converts matter to energy more efficiently than a black hole's accretion disk. Gas spiraling inward can radiate up to 40% of its mass as energy, far more than nuclear fusion in stars. These glowing disks power quasars, some of the brightest objects ever seen, shining across billions of light years. The engine is simple, gravity compressing matter until light is squeezed out in every direction. To understand why black holes produce such extraordinary power, we need to look at what happens long before matter crosses the event horizon. The true engine is not inside the black hole, it forms in the space around it. When gas clouds, stars, or even interstellar dust drift too close, they are not swallowed immediately. Instead, they swirl into a rotating whirlpool of matter, flattening into a thin, luminous disk. This disk, the accretion disk, is where matter is heated, compressed, and torn apart with such intensity that it radiates more energy per gram than any other known process. This is the first quiet truth. A black hole is brightest at its edges, not its center. The black hole itself emits no light. But the material orbiting it glows like a miniature sun, heated to tens of millions of degrees by friction, collisions, and the violent tug of gravity. This glow can outshine galaxies. It can reach across intergalactic space. It can illuminate the universe's earliest epochs. So why is this landing zone so efficient? The answer lies in motion, specifically the way matter accelerates as it orbits a steep gravitational curvature. In ordinary space, falling feels like a simple descent, but near a black hole, falling becomes a rapid spin. Matter accelerates to a significant fraction of the speed of light, and when something moves that fast, its energy climbs steeply. At these speeds, even tiny collisions release enormous amounts of heat. Gas molecules slam into each other, magnetic fields twist and reconnect. Turbulence churns like a cosmic storm. The heat becomes radiation, X-rays, gamma rays, ultraviolet light, and all of this radiation escapes outward long before the matter crosses the point of no return. In this sense, black holes do not consume without giving. They shine by shredding the matter they feed on. Compare this to the energy released by nuclear fusion, the process that powers every star. When hydrogen fuses into helium in stellar cores, about 0.7% of the hydrogen's mass becomes energy. That number seems small, yet it fuels galaxies. But an accretion disk can convert up to 10, 20, even 40% of a particle's mass into radiation, depending on how fast the black hole spins. A rapidly spinning Kerr black hole creates a deeper gravitational well, allowing matter to orbit closer before falling in. The closer the orbit, the higher the efficiency. In other words, the spin of a black hole acts like a throttle. The faster the spin, the brighter the engine. But the story grows even more fascinating. As matter spirals inward, magnetic fields are twisted like rubber bands. When they snap, they fling energy outward in the form of jets, narrow beams of plasma accelerated to near light speed and launched along the black hole's rotational axis. These jets can stretch for thousands of light years, piercing through galaxies like luminous spears. They transport enormous amounts of energy into surrounding space, heating gas, sculpting galaxies, and even regulating star formation. Black holes, through these jets, control the growth of galaxies. They are not just engines, they are architects. This is especially dramatic in quasars, the most luminous black hole engines in the universe. A quasar is simply a supermassive black hole consuming matter at a tremendous rate. As the disk heats, the radiation becomes so powerful that it can be seen from 13 billion light-years away. These distant quasars allow us to peer into the early universe, observing galaxies that formed when the cosmos was still young, still assembling itself out of cold hydrogen gas. Yet, behind all this power is something remarkably simple: gravity dragging matter inward and matter resisting by heating itself. Friction, turbulence, and magnetic pressure create the glow, but gravity sets the scale. Gravity is the hand on the wheel. Gravity compresses matter until the heat becomes unbearable. Gravity pulls electrons from atoms, atoms from molecules, and molecules from dust. And all of that energy is released as radiation. The closer matter gets to the black hole, the hotter it becomes. By the time it reaches the inner edge of the disk, it can be millions of degrees. At these temperatures, atoms are stripped into ionized plasma. Electrons and nuclei flow separately, guided by magnetic fields. This plasma is electrically conductive, turbulent, and intensely bright. But not all the light escapes. Some of it spirals inward. Some of it bends around the black hole, completing partial orbits before flying outward again. Some of it forms the photon sphere, a region where light can circle the black hole like a planet orbits a star. The image captured by the Event Horizon Telescope in 2019 shows this glowing swirl of trapped light, forming a ring around the black hole's shadow. This ring is the visual signature of extreme efficiency. Matter that emits light here is moving so fast and being compressed so powerfully that almost half of its mass energy can be radiated before crossing the horizon. Nothing else in nature, not stars, not supernovae, not even neutron stars, comes close. But efficiency is not only about brightness, it is also about influence. The energy pouring out of accretion disks can impact entire galaxies. In some cases, the jets driven by supermassive black holes are powerful enough to blow out the gas in the center of galaxies, suppressing star formation for millions of years. In other cases, the jets compress gas clouds, triggering star formation instead. Black holes therefore act as regulators, alternating between feeding and restraining their host galaxies. This is one of the universe's quiet symmetries. The engines that destroy are also the engines that build. And yet, for all their power, black holes are fundamentally simple. They follow Einstein's field equations. They obey the conservation of angular momentum. They accrete matter according to predictable disks, shaped by magnetic turbulence and gravity. They do not choose to shine or to tear matter apart. They simply follow geometry, and geometry does the rest. But the geometry is breathtaking. Consider a particle on the edge of a rapidly spinning black hole. It is caught in a frame-dragging effect where space itself rotates. In this region, known as the ergosphere, even a stationary observer cannot remain still. Space-time forces them to rotate with the black hole. Within this swirling region, energy extraction becomes possible. Matter can enter the ergosphere and leave with more energy than it came with. This process, described by Roger Penrose, hints that black holes may not just convert matter to light, but also tap into their own rotational energy. In other words, black holes are engines not only of the matter they consume, but potentially of their own spin. Everywhere we look, black holes exceed expectations. They regulate galaxies, they power quasars, they accelerate particles to energies far beyond what human machines can achieve. They shine brilliantly just outside their own darkness. And as we continue drifting through this journey, one question follows softly in the background. If black holes can release so much energy at their edges, what secrets lie deeper inside, where energy can no longer escape at all? Part 6. What is the singularity really made of? A singularity is not a physical point we can describe. It is a limit in our equations, a place where density becomes infinite and space-time curvature becomes undefined. It is where general relativity stops working, where quantum mechanics should take over, but we do not yet know how. The singularity is the universe whispering, "There is more to learn." To approach the concept of a singularity, imagine walking into a library filled with every book ever written: astronomy, physics, mathematics, philosophy. Yet, every time you reach the final chapter of any subject, the last pages fade into blankness. The story stops, not because it ends, but because we have not written the language needed to describe it. That is what a singularity represents: the blank pages at the edge of our understanding. General relativity, Einstein's great geometric description of gravity, works astonishingly well everywhere else. It predicts gravitational waves. It explains the orbit of Mercury. It describes how time bends near mass, how light curves around stars, how planets follow the shape of space-time. But near the center of a black hole, its equations begin to diverge. spiking into infinities that have no physical meaning. Physics is not supposed to give you infinity as a final answer. Infinity is a placeholder, a signpost that says, this is where your map ends. The singularity lies at that boundary. Imagine falling into a supermassive black hole. You pass the event horizon without noticing. You drift inward. Tidal forces remain gentle at first. Time begins to stretch. Light bends strangely. But deep inside, the curvature of space-time begins to rise sharply, holding tighter and tighter around you. Distances stretch and compress in ways your senses cannot decode. The fabric of space shrinks inward, like cloth being gathered into a single point. If general relativity were the only guide, it would tell you that eventually you reach a region of infinite curvature, a place where space-time is crushed to zero width and all matter collapses into a point of infinite density. But even Einstein himself suspected this description was incomplete. He knew that the universe does not hand out infinities casually. Infinities are warnings, not destinations. This is where quantum mechanics should step in. But the quantum theory we have today describes particles on flat static space, not on the violently curved spacetime inside a black hole. The deeper you fall, the more quantum mechanics and general relativity clash. One suggests discreteness, tiny packets of energy, finite quantities. The other predicts smoothness, continuous curvature, geometry without steps. As you approach the singularity, these two worldviews no longer agree. What lies at the center is not something infinite, it is something unknown. Some physicists believe the singularity is a region where space-time breaks down into discrete atoms, or quanta of geometry, tiny loops or threads that form a granular structure. This idea is explored in loop quantum gravity. In such a picture, the singularity is not a point at all. It is a compressed form of space where the concept of distance becomes meaningless. You cannot say here or there because space itself has dissolved. Other theories imagine that the matter inside a black hole does not collapse to a point, but to an extremely dense core, something like a Planck-scale object smaller than any particle we can describe. This Planck star would resist further collapse through quantum pressure, much like how neutron stars resist collapse through degeneracy pressure. In these models, the singularity is replaced by a finite-size object, impossibly dense, held together by the quantum structure of spacetime. There are even hypotheses in which the singularity rebounds, creating a new region of spacetime, a new universe inside the black hole. In this interpretation, every black hole could be the seed of another cosmos, and our universe might reside inside a black hole within a larger parent universe. It is speculative, but mathematically possible. The singularity becomes not an end, but a bridge, not destruction, but rebirth. But let's return to what we can say confidently. As you approach the singularity, every direction in space begins to point inward. Time itself narrows toward a single outcome. The tidal forces become overwhelming. The gravitational gradients grow enormous. You become aligned with the curvature of space-time, stretched along the direction of fall. This is not because gravity wants to tear you apart. Rather, the geometry around you is too sharply curved to allow any other orientation. The very structure of the universe compels you into a shape consistent with spacetime's most extreme configuration. But even this dramatic description breaks down as you get closer. Eventually, the tidal forces become so large that quantum effects cannot be ignored. Particles begin to fluctuate wildly. Distances become uncertain. The idea of a well-defined position loses meaning. The classical description of gravity, smooth, curved spacetime, dissolves into a quantum foam, chaotic and flickering. This chaotic region, sometimes called the Planck regime, is where we believe the singularity lives, not as a point, but as a zone where the familiar concept of spacetime no longer applies. If you could look at this region with perfect vision unfazed by gravity or quantum turbulence, it might appear not as a point but as a roiling storm of geometry, loops of space forming and dissolving, pockets of time opening and closing. The very dimensions you rely on to navigate reality would warp and stutter. It would be the breakdown not of matter, but of the stage on which matter exists. The singularity is the ultimate boundary of experience. Even the laws of physics behave differently when discussing it. When general relativity tries to describe the singularity, it produces infinite curvature. When quantum mechanics tries to describe it, it demands space-time be quantized. Neither description is fully right, neither can be discarded. The singularity sits at the intersection, a meeting point of two incomplete theories. What emerges from this intersection is the greatest open question in theoretical physics. This is why black holes remain so mysterious. They are the only objects in the universe where known physics guarantees its own failure. Not because the black hole disobeys the laws, but because the laws contradict each other at the extreme. The singularity is a mirror held up to our ignorance. It is where the universe says, "You understand much, but not everything." And yet, this ignorance is productive. Every attempt to understand the singularity has pushed physics forward. It has inspired the search for quantum gravity. It has raised questions about the nature of space, the nature of time, and the fate of information. It has linked black holes to thermodynamics, entropy, and even holography. The singularity is not a blank spot on the map, it is a fertile frontier. But perhaps the most poetic truth is this: the singularity is not a thing. It is a failure, a sign that our equations must evolve. It is the breakdown of the story just before the next chapter begins. And as we drift deeper into this quiet journey, another question slowly comes into focus. If the singularity challenges the limits of physics, then what happens to the information carried by everything that falls in? Part 7. Do black holes have a temperature? In the 1970s, Stephen Hawking discovered that black holes are not perfectly black. They emit a faint glow, Hawking radiation, caused by quantum fluctuations near the horizon. This means black holes have a temperature, and over unimaginable spans of time, they evaporate. Even something so dark carries a quiet warmth. To understand this strange warmth, imagine drifting near the edge of a black hole, not close enough to fall in, but near enough to feel the deep curve of space-time beneath you. To general relativity, this region is smooth, silent, and empty. But to quantum mechanics, it is anything but empty. Quantum fields never rest. Even in a perfect vacuum, they flicker, they jitter. They produce pairs of virtual particles that appear briefly, then annihilate each other, fading back into the field. Under ordinary circumstances, this dance is invisible. The virtual particles appear and vanish too quickly to leave a trace. But near a black hole's horizon, the geometry of spacetime becomes dramatic enough to interfere with this dance. One particle in the pair can fall inward while the other escapes outward. The escaping particle becomes real. It leaves with energy. The infalling particle carries negative energy relative to the outside universe. To conserve energy, the black hole loses mass. This is Hawking radiation, a quiet glow produced not by the black hole itself, but by the structure of quantum fields around it. The black hole is not burning or leaking in any classical sense, it is interacting with the vacuum. The temperature of this glow depends on the size of the black hole. Large black holes are cold, small ones are scorching. A black hole with the mass of the Sun has a temperature of about 1/10 millionth of a Kelvin, far colder than the cosmic microwave background that fills the universe. Such a black hole absorbs more heat from the universe than it emits. It grows slowly, gathering mass from the surrounding temperature field. But a tiny black hole, perhaps the mass of a mountain, would glow fiercely with Hawking radiation. Its temperature could reach millions or billions of degrees. It would evaporate quickly, releasing a burst of energy in its final moments. We have never observed such small black holes, but the math predicts their behavior with haunting clarity. The idea that black holes can evaporate shocked the scientific community. Until Hawking's calculation, black holes were thought to be eternal. Once formed, they would remain forever, silent and unchanging. Hawking radiation changed everything. It showed that black holes obey the laws of thermodynamics. They have entropy, they have temperature. They behave like physical objects, not just geometric curiosities. This connection between gravity, quantum mechanics, and thermodynamics is one of the most profound discoveries in physics. It suggests that black holes are not simply dead ends in the fabric of spacetime. They are thermal objects with a subtle life cycle. But to understand why black holes have temperature, we must turn to the quantum vacuum itself. The vacuum is not empty. It is a sea of fields at their lowest possible energy. These fields fluctuate because of the uncertainty principle. The more you try to contain or measure a region of space, the more energy it seems to hold. Near the horizon of a black hole, this confinement becomes extreme. Space is stretched, time slows. Virtual particles behave differently because the background against which they flicker is no longer uniform. The gravitational gradient, the difference in curvature from one side of the horizon to the other, creates a separation between virtual particles. What was once a pair becomes two distinct trajectories, one inward, one outward. The outward particle becomes a photon or a particle of matter carrying a tiny bit of the black hole's energy with it. But what does the infalling particle do? It reduces the black hole's mass. Negative energy is a strange concept, but it is necessary in the mathematics. It ensures that the total energy of the system remains conserved. Every photon emitted outward subtracts mass from the black hole. Over billions or trillions of years, this slow trickle becomes significant. A black hole will shrink, cool, then suddenly heat up as it becomes small enough for its temperature to rise sharply. It evaporates faster and faster, ending in a final burst of radiation. This entire life cycle is called black hole evaporation. But evaporation is so slow for supermassive black holes that they will outlive stars, galaxies, and even atoms. When the universe grows old and cold, when starlight fades and galaxies drift apart, black holes will remain as the final luminous engines in a darkening cosmos. Their Hawking radiation will be one of the last sources of light, one of the last dynamic processes happening in a universe otherwise falling into stillness. This gives Hawking radiation a poetic resonance. It is the quiet warmth of an object that should be perfectly cold, the faint glow of something that should be entirely dark. A reminder that even the most extreme structures obey the laws of physics. But the existence of temperature raises deeper questions. Thermodynamics tells us that every warm object has entropy, a measure of disorder, or more precisely, a measure of the number of microscopic states hidden beneath the surface. Entropy is what drives heat to spread out, what causes time to have a direction, and what links the physics of information to the physics of matter. If a black hole has a temperature, it must have entropy, and it does. In the 1970s, physicist Jacob Bekenstein calculated that the entropy of a black hole is proportional to the area of its event horizon, not its volume. This is extremely strange. Most objects store information in their interior. A black hole appears to store information on its surface. This insight led to something extraordinary, the holographic principle. The idea that the information inside a region of space may be encoded on its boundary. In other words, everything inside the black hole might be represented on the horizon. The surface becomes a kind of cosmic ledger, recording whatever has fallen inside in a way we do not yet fully understand. This insight links gravity to quantum mechanics in a way rarely seen. It connects geometry, information, entropy, and temperature. And all of it begins with Hawking radiation, the faintest whisper of light from the darkest object in the universe. But this whisper is not just a glow. It is a clue that spacetime is not just a stage for matter to move across. It is a dynamical structure that interacts with quantum fields. It vibrates, it fluctuates, it participates in the thermal behavior of the cosmos, and it raises a deeper question still. If black holes evaporate, what happens to the information carried by the things that fall inside them? This is the heart of the information paradox, one of the greatest puzzles in all of physics. It arises naturally from the temperature of black holes, because anything with temperature radiates, and anything that radiates might lose information. But quantum mechanics says information cannot be destroyed. Between these two truths lies one of the deepest mysteries in science. As we drift forward, we step quietly toward this next question, toward the paradox at the core of black hole physics, where temperature, entropy, and the fate of information meet. Part 8. Can black holes connect different regions of space? Einstein's equations allow solutions that look like tunnels, wormholes, bridging distant points in spacetime. Whether they exist physically is unknown, but the mathematics hints at a universe more flexible than we imagine. Black holes may be entrances to these tunnels, but if so, they are unstable and short-lived. Still, the possibility that spacetime can fold in such a way is a reminder that the cosmos plays with geometry on scales we barely understand. To understand this possibility, picture spacetime not as a rigid grid, but as a fabric, soft, pliable, capable of bending, stretching, and curving. Gravity shapes this fabric, creating wells where mass sits and valleys where energy flows. Most of the time, these curves are gentle. But under extraordinary conditions like those surrounding black holes, the curvature becomes so dramatic that Einstein's equations begin to suggest exotic pathways. A wormhole is one such pathway. It is a hypothetical bridge connecting two distant regions of spacetime. If you could travel through it, the journey from one end to the other might take moments, even if the two ends are separated by thousands or millions of light years. In principle, the wormhole could even connect different universes or different times. This is not fantasy. It is a legitimate implication of general relativity. But the story is more subtle than it first appears. Einstein's equations do not forbid wormholes. They merely describe what happens if spacetime is folded in a certain way. The question is not whether the math allows such tunnels. The question is whether nature does. One early solution that hinted at these tunnels was the Schwarzschild wormhole, also called the Einstein-Rosen bridge. It emerges naturally from the equations governing a non-spinning black hole. But this bridge pinches off too quickly to allow anything, matter, light, even information, to pass through. It is not a tunnel for travel. It is a mathematical structure, not a physical passage. Still, the idea stuck because it revealed something extraordinary. Spacetime is capable of connecting regions that would otherwise appear separate. Later solutions, such as the Kerr metric describing spinning black holes, opened the door to even wilder possibilities. A rotating black hole does not collapse into a point-like singularity. Instead, it forms a ring-shaped singularity. And the geometry around this ring is complex, so complex that it seems to offer routes through the interior. Some of these routes would exit not into the same universe, but into entirely different regions of spacetime. But before your imagination takes off, there is a caveat, perhaps the most important one. Every known wormhole solution for real, physical matter is unstable. Any traveler entering such a tunnel would find it collapsing faster than it could be crossed. The slightest perturbation, light, gravity, even the presence of the traveler, would cause the wormhole to pinch closed. It's as if spacetime briefly entertains the possibility of making shortcuts, then quickly retracts them. This fragility leads to an intriguing question. Could something stabilize a wormhole? Could exotic matter with negative energy, hold the throat open? In theory, negative energy exists. Quantum fields can produce it for brief moments. Even Hawking radiation involves particles with negative energy falling into black holes. But using such energy on large scales to stabilize a wormhole remains purely hypothetical. If it were possible, it would require physics far beyond what we currently understand. Still, the possibility is there, quietly waiting in the equations. But before we drift too far into speculation, let's return to the black hole itself. Could a black hole naturally connect to a white hole, a theoretical object where matter can escape but cannot enter? A black hole pulls matter in, a white hole pushes matter out. Joined together, they form a wormhole-like structure. This idea appears in several solutions to Einstein's equations, but white holes have never been observed. They might be physically impossible. Their stability is deeply questionable, and they would violate thermodynamics unless they exist in very special conditions. So while the idea is mathematically elegant, nature may not construct such objects in reality. Still, something about the concept continues to entice physicists. It is the sense that spacetime is not as fixed or rigid as it seems. We tend to imagine the universe as a vast grid, 3 spatial dimensions and 1 timeline, stretching uniformly in all directions. But general relativity shows that spacetime is dynamic. It bends around matter, it twists around rotation, it expands, contracts, and reacts to energy. And if something can bend, it can, in principle, fold. Wormholes are not a glitch in the equations, they are a natural expression of a flexible universe. There's another perspective to consider: quantum gravity. Many physicists suspect that wormholes might exist not as large, traversable tunnels, but as tiny, fleeting connections at the quantum scale, micro-wormholes appearing and disappearing in the quantum foam. These microscopic bridges would be far too small for matter to pass through, but they suggest that the topology of spacetime is far richer than our everyday intuition allows. In some versions of the holographic principle, spacetime itself may be woven together through networks of quantum entanglement. In such theories, wormholes may not be structures you travel through. They may be the geometry of connectivity between quantum states. Even the famous EPR conjecture proposes that entangled particles might be connected by extremely tiny wormholes, non-traversable but deeply meaningful. In this view, wormholes are not shortcuts. They are signatures of entanglement. Spacetime is knit together by threads of quantum connectivity. It is a radical idea, but it brings together two realms of physics, gravity and quantum mechanics, that have resisted unification for nearly a century. Now, let's imagine the experience. Suppose for a moment that traversable wormholes did exist. What would it feel like to enter one? You would not see a tunnel in the usual sense. You would see the geometry of space curve around you. Distances would warp. Directions would bend. You might cross the throat of the wormhole in seconds while emerging light years away. You would not travel faster than light. You would simply take a different route through spacetime. But again, this scenario is speculative. It rests on physics that we do not yet possess. The equations allow it, but nature may not. There is a quiet beauty in that uncertainty. Wormholes sit at the intersection of what we know and what we hope to understand. They are bridges not just between places, but between ideas, between the mathematics of relativity and the mysteries of quantum gravity. Even if the universe does not allow stable wormholes, the fact that they appear naturally in the equations tells us that spacetime is far stranger, far more adaptable, and far more creative than we once believed. And as we continue drifting through this journey, one gentle question unfolds before us. If spacetime can fold in such exotic ways, what role does rotation play in shaping the deeper geometry of black holes in the cosmos around them? Part 9. Why do galaxies need black holes at their centers? Nearly every galaxy, including our own, orbits a supermassive black hole, tens of thousands to millions of times the mass of the Sun. These giants shape the flow of stars, anchor galactic structure, and regulate star formation through their energetic outflows. Without them, galaxies would be less organized, less stable, a reminder that something incredibly dense is holding the cosmos together. To understand why galaxies need these central giants, imagine a galaxy not as a static picture, but as a vast swirling ecosystem, hundreds of billions of stars drifting clouds, of gas, lanes of dust, dark matter halos, and quiet pockets where new stars are born. Nothing in this ecosystem stands still. Everything moves, everything orbits, everything responds to gravity's subtle choreography. And in the heart of this motion sits something impossibly dense, a supermassive black hole. Its presence is not decorative, it is structural. The entire galaxy grows, bends, rotates, and evolves in response to this central mass. Without it, the galactic disk would be looser, the arms would be less defined, the rhythms of star birth and star death would be more chaotic. The black hole does not simply sit at the center of a galaxy, it anchors the galaxy. It gives the disk a gravitational reference point, a center of mass around which everything else slowly turns. But this anchoring is only part of the story. Supermassive black holes are not passive. They influence their galaxies across billions of years, shaping their evolution in ways both subtle and dramatic. Let's drift into one of the quiet truths. A supermassive black hole is tiny compared to its galaxy. but its influence is immense. The black hole at the center of the Milky Way, Sagittarius A, is about 4 million times the mass of the Sun, but the galaxy around it is over 1 trillion times more massive. The black hole is only a speck compared to the whole. But gravity does not distribute its influence evenly. A small, incredibly dense mass can sculpt the dynamics of a system much larger than itself. Think of a marble controlling the path of a river by sitting at a crucial point in the flow. The marble is small, but the river must bend around it. Something similar happens with black holes. Their gravity sculpts the inner structure of galaxies, guiding the motions of stars and influencing the patterns of rotation. Observations of stars near Sagittarius A reveal them whipping around the center at thousands of kilometers per second. Only something immensely compact could cause such motion, and this compactness stabilizes the galactic core, keeping it organized. But gravity alone does not explain why galaxies need black holes. Their energetic output is equally important. When matter falls into a black hole, it heats up, forming a bright accretion disk. During periods of high feeding, when a galaxy funnels large amounts of gas into its core, the black hole emits powerful jets of radiation and particles. These outflows travel far beyond the galaxy's center, affecting star formation on a galactic scale. Imagine a black hole acting like a cosmic thermostat. When a galaxy has too much gas collapsing into stars too quickly, the central black hole awakens. Its jets heat and stir the gas, pushing it outward, preventing runaway star formation. This maintains a balance between too many stars and too few. Without this regulation, galaxies could burn through their gas too quickly, producing a brief burst of stars followed by billions of years of darkness. This feedback mechanism, known as AGN feedback, active galactic nucleus feedback, is now considered essential to galaxy evolution. Simulations of the universe do not resemble the galaxies we see unless this feedback is included. In other words, without central black holes, galaxies in our universe would not form correctly. A black hole does not simply sit at the center, it governs. This governance extends to shaping the dark matter halo around a galaxy. Although dark matter outweighs normal matter by a significant margin, the presence of a supermassive black hole influences how the halo contracts or expands over cosmic time. The feedback from the black hole's jets and radiation can rearrange both visible and invisible matter, creating the gravitational environment in which stars form and orbit. Consider the early universe. Billions of years ago, when galaxies were first forming, supermassive black holes were voracious. They consumed gas at extraordinary rates. Their jets lit up the young cosmos as quasars, beacons so bright they could be seen across immense distances. These quasars injected energy into the forming galaxies, shaping their architecture from the inside out. A galaxy without a supermassive black hole would be like a city without a structural foundation, still recognizable, but far less organized, far less stable. Another quiet truth: galaxies and black holes grow together. Observations show a tight correlation between the mass of a galaxy's central black hole and the mass of its surrounding bulge of stars. This relationship holds across different galaxies, across different environments, across cosmic history. It is not random. It suggests that galaxies and their black holes co-evolve, influencing each other's growth in a delicate, interwoven dance. As galaxies accrete matter, their black holes accrete as well. As black holes emit radiation and jets, galaxies respond, sometimes shrinking their star formation, sometimes pushing gas outward, sometimes triggering new waves of collapse and birth. Each shapes the other. This shared evolution tells us something profound. The center of a galaxy is not separate from its structure. It is part of its identity. Galaxies are not randomly assembled clusters of stars. They are ecosystems with central engines. And so the question becomes, why does the universe form these central engines at all? Why do galaxies almost always host black holes? One answer lies in the earliest epochs of cosmic history. After the Big Bang, matter began clumping under gravity. Small overdensities collapsed into stars, and some of those first stars were massive enough to collapse into black holes. These early black holes grew quickly, feeding on the dense gas of the young universe. By the time galaxies formed, many of them already had central black holes in place. But another answer is more geometric. Black holes are simply the natural outcome of mass collapsing under gravity. If you gather enough matter in one place, it will eventually form a black hole. Galaxies gather matter. Therefore, galaxies create black holes. But galaxies do not merely create black holes, they seem to need them. The presence of a black hole stabilizes the central region, regulates gas flow, and sets the scale of stellar motion. It gives galaxies structure, it gives them purpose, it gives them coherence across billions of years. And perhaps the most poetic truth is this: a supermassive black hole sits at the heart of a galaxy, not as a destroyer, but as a kind of anchor. Its gravity holds the center together, its energy shapes the spiral arms, its feedback balances the life and death of stars, its presence keeps the galaxy from collapsing into chaos. It is not the absence of light that defines it, it is the presence of structure it grants to everything around it. And as we drift forward in this quiet journey, another question gently rises. If black holes help shape galaxies, how do we observe something that gives off no light, but moves entire worlds around it? Part 10. How do we see something that gives off no light? We observe black holes through their influence. We watch stars orbit an invisible mass. We measure gravitational waves from distant collisions. We capture the silhouette of a shadow against a glowing disk, as the Event Horizon Telescope did in 2019. The black hole itself remains unseen, but its presence is unmistakable, traced in the motion of everything around it. A black hole cannot be seen directly because light cannot escape it. No matter how brightly the universe glows, no matter how many photons rush outward from quasars or nebulae or colliding stars, once light crosses the event horizon, it is lost to us. It does not bounce back. It does not scatter. It does not even whisper. And so, to observe a black hole, we must look not at the object itself, but at the geometry it carves into its surroundings. Imagine holding a clear marble under sunlight. You cannot see the marble directly. What you see is the way light bends around it. Black holes behave in a similar way, but with gravity instead of glass. They warp space, they bend light, they distort paths, and these distortions become the quiet outlines of their existence. One of the most common ways we detect black holes is by watching how stars move around them. In the center of the Milky Way, astronomers have spent decades tracking the orbits of dozens of stars. These stars swing around an invisible point like comets around the sun, their speeds and trajectories revealing the gravitational pull of something incredibly dense. From the timing of their orbits, scientists can calculate the mass of this invisible object, about 4 million suns. Nothing else could fit inside the small region they orbit. No star, no cluster, no gas cloud, only a supermassive black hole. This method is elegant. We see the black hole by the motion it commands. But black holes also announce themselves through their meals. When gas and dust fall inward, the material heats up, forming an accretion disk that shines spectacularly. These disks can radiate in X-rays, ultraviolet light, optical wavelengths, and radio waves. The black hole itself remains dark, but the space around it becomes a lighthouse. Telescopes like Chandra and XMM Newton study the high-energy glow from these disks, revealing black holes in distant galaxies. If you see a point in the sky producing enormous amounts of X-rays from a space no larger than our solar system, it is almost certainly a black hole feeding. The idea is simple. To see a black hole, look at what it is doing to the matter around it. Even isolated black holes, those not feeding on a disk, can sometimes be found by the way they bend background light. This effect is known as gravitational lensing. When a black hole passes in front of a distant star, the star's light bends around the black hole, creating a temporary brightening or distortion. It is like watching a pebble dropped into a stream and seeing the water flow around it, revealing the pebble's shape without ever seeing the pebble itself. Gravitational lensing is subtle and requires precise timing, but it offers a glimpse of black holes wandering through interstellar space, dark travelers detectable only by the way they sculpt the paths of distant photons. But perhaps the most dramatic method of detection came in 2015, when the LIGO detectors captured the first gravitational waves, ripples in spacetime, from two merging black holes. These waves traveled for over 1 billion years before reaching Earth. They were not flashes of light, they were tremors in the fabric of existence. The way spacetime stretched and compressed allowed scientists to calculate the masses of the colliding black holes, their spin, and the moment they fused into a single, larger black hole. This was the first time humanity heard the universe rather than saw it. Gravitational waves expanded our senses. They proved that even without light, the curvature of spacetime itself can tell us where black holes are, what they are doing, and how they are evolving. But the most iconic visual evidence of a black hole came in 2019, the image of the black hole in the galaxy M87, captured by the Event Horizon Telescope. This image was not a direct photograph. It was a reconstruction built from radio signals gathered by telescopes scattered across the Earth. By combining their observations, scientists created a virtual telescope the size of our planet, providing the resolution needed to see the shadow of a black hole for the first time. What appeared was a glowing ring of light surrounding a dark center. The dark center is not the black hole itself. It is the shadow, the region where light cannot escape. Around it, the bright ring is the last orbiting light, swirling just outside the event horizon. Some of this light circles the black hole multiple times before escaping toward Earth. Some of it falls inward. Some of it bends so dramatically that it reaches us from behind the black hole, creating a warped, luminous halo. This image is not merely a scientific achievement, it is a portrait of gravity's deepest curve. The fact that we can resolve such a shadow from 55 million light-years away is a reminder that black holes, while invisible, leave behind unmistakable signatures. We see them not by illumination, but by interruption, not by brightness, but by bending, not by presence, but by influence. There's another method too, one that feels almost poetic in its subtlety. Black hole jets. These narrow beams of charged particles shoot out from the poles of rapidly spinning black holes, accelerated by magnetic fields in the accretion disk. They can travel for thousands of light years, punching through the interstellar medium. When we see a jet slicing through space, bright against the dark, we know a black hole is feeding at the other end. Even the jet, however, does not emerge from the black hole. It emerges from the space around it, where magnetic fields twist and release stored energy. The black hole remains invisible, but the universe around it glows with its presence. Of course, some black holes are quiet. No jets, no disks, no bright companions. These are the hardest to find. But even they are not perfect secrets. When such a black hole drifts through a region rich with stars, it reveals itself through microlensing. When it interacts with a companion star, we see the star's orbit wobble. When it spins space around itself, it creates frame-dragging effects measurable with precise instruments. Every method tells the same story. We cannot see the black hole, but we can see its footprint. This is a pattern at the heart of astrophysics. Some of the most important structures in the universe announce themselves through absence. Dark matter, dark energy, neutrinos, black holes, each is invisible in some way. But each leaves a trace, a pull, a vibration, a bending, a distortion, a glow. The universe is generous with clues, even when it is stingy with light. And so the question remains, how do we see something that gives off no light? By watching how the universe behaves around it, by following the paths of stars, by listening to the tremors in spacetime, by capturing the shadow cast against a bright background, by tracing the architecture of curved light. We see black holes the way we see wind, not directly, but through motion and pattern. And as we drift onward in this quiet exploration, another gentle question rises. If black holes can be traced only through their influence, how do they themselves come to spin? And what does that spin do to the spacetime around them? Part 11. Why do black holes spin? Every star that collapses carries angular momentum. When that mass is compressed into a smaller volume, the rotation speeds up, just as an ice skater spins faster by pulling in their arms. A spinning black hole drags space-time around, with it twisting the paths of nearby objects and altering the shape of the event horizon. In their rotation, black holes become even more potent time machines. To understand why black holes spin, we must begin long before they form, when the universe itself was young, filled with swirling clouds of gas and dust. Motion is not rare in the cosmos. Everything turns, everything drifts, everything carries momentum inherited from the early jitter of matter after the Big Bang. Stars form from collapsing clouds, and these clouds rotate. Even if the spin is slight, conservation of angular momentum ensures that as they collapse into denser shapes, their rotation increases. A star, for all its brilliance, is not a stationary object. It turns steadily, slowly, across millions of years, and because angular momentum must be conserved, cannot be created or destroyed, the rotation the star had does not vanish when it collapses at the end of its life. Instead, it is amplified. The collapsing star becomes smaller, its radius shrinks, its mass compresses inward, and the spin grows faster, much faster. This increase is dramatic, not subtle. A star rotating once every month might produce a black hole rotating hundreds of times per second. The spin parameter, a way physicists measure a black hole's rotation, can approach the theoretical limit where the black hole's rotation is so fast that the event horizon itself becomes flattened and oblate, bulging at the equator and narrowing at the poles. This is the first quiet truth. Black holes spin because the stars that made them spun. But their rotation does not stop there. Black holes can gain additional angular momentum by consuming orbiting matter. Gas spiraling inward through an accretion disk brings angular momentum with it. As this matter falls into the black hole, the rotation of the disk becomes the rotation of the black hole. A steady diet of swirling matter can spin a black hole up to extraordinary speeds. Some black holes rotate so rapidly that space-time around them twists like a cosmic whirlpool. This frame-dragging effect, predicted by general relativity and confirmed near Earth by experiments like Gravity Probe B, becomes extreme near a spinning black hole. Space-time itself is pulled around. You cannot remain stationary near such an object. Every object is forced to rotate with it. Even light must twist around the spinning geometry. The region where this occurs is called the ergosphere, a teardrop-shaped space outside the event horizon. Inside the ergosphere, nothing can stand still relative to a distant observer. The fabric of space-time is being dragged along too quickly. Motion, here, is not optional. It is a consequence of geometry. This dragging has profound consequences. It means that energy can be extracted from a spinning black hole. Roger Penrose showed that if a particle enters the ergosphere and splits into two, one falling in and the other escaping, the escaping particle can carry more energy than the original. This process drains rotational energy from the black hole, slowing its spin. It is as if the black hole's rotation can be tapped like a cosmic flywheel. This extraction process is not just theoretical. It may be one of the reasons some black holes produce jets, narrow beams of plasma accelerated to extreme energies that shoot out from the poles. In these jets, magnetic fields twisted by the black hole's rotation act like particle accelerators, flinging charged particles at near light speed across thousands of light years. Rotation, in this sense, becomes a source of cosmic violence and cosmic structure. It is the engine behind some of the most energetic phenomena ever observed. But the spin of a black hole also alters its shape. A non-rotating black hole is perfectly spherical, its horizon a smooth sphere in space-time. A spinning black hole is flattened, bulging at the equator due to rotational effects. This difference changes the distances matter can orbit safely. A spinning black hole allows matter to orbit closer to the horizon before plunging inward. This means the accretion disk becomes hotter. The radiation becomes brighter. The efficiency of energy conversion increases. Spinning black holes glow more fiercely than their non-spinning cousins. This ties directly into why they act as time machines. Near a spinning black hole, time does not simply slow due to gravity, it twists. The dragging of spacetime alters the flow of time itself. If you orbit in the direction of the black hole's spin, you can skim closer to the horizon than if you orbit against it. The spin either helps or hinders you, depending on your direction. This asymmetry means the passage of time differs for two observers, taking opposite paths around the black hole. One could return after a short journey to discover that far more time has passed for the other. Their clocks, once synchronized, would no longer agree. Spin becomes another dimension of time dilation. But how fast can a black hole spin? There is a theoretical upper limit. If a black hole spins too quickly, approaching what physicists call the extremal limit, centrifugal force within the equations cancels out gravitational collapse at the poles. In this state, the horizon would shrink toward zero size. Nature seems to forbid black holes from reaching or exceeding this limit. Interactions with matter, radiation, and quantum effects always slow them down before they cross it. Still, many black holes spin extraordinarily fast. Some stellar mass black holes rotate at more than 95% of the theoretical maximum. Some supermassive black holes spin similarly, their enormous frames turning like colossal cosmic gyroscopes. Where does all this spin go? What does all this rotation mean? In the far future, after a black hole stops feeding, after galaxies grow quiet, after stars fade and gas cools, the spin of the black hole will slowly decrease. Hawking radiation, which causes black holes to evaporate over unimaginable timescales, carries away angular momentum as well as mass. The black hole's spin fades with its evaporation. Eventually, it slows, cools, shrinks, and vanishes. But this process takes longer than the current age of the universe by many orders of magnitude. For now, black holes remain some of the fastest spinning objects in existence. They rotate, they twist spacetime, they shape the paths of light, they power jets, they influence the structure of galaxies, they alter the flow of time itself, and through their rotation, they remind us of a deeper truth woven into the universe. Motion never fully stops. The spin a star inherits from the early cosmos does not die, it intensifies. Collapse accelerates rotation, feeding enhances it, geometry expresses it. A black hole is not the end of motion, it is the place where motion becomes profound. And as we continue drifting deeper into this quiet cosmic journey, another gentle question begins to form. If black holes twist time and space so dramatically through their spin, what happens when two of them collide and merge into one? Part 12. What happens when two black holes collide? When two black holes spiral together, they radiate energy in the form of gravitational waves, ripples in space-time first detected in 2015. In the final moments before merging, they distort each other's horizons and warp time itself. The result is a single, larger black hole and a burst of gravitational energy that travels across the universe like a quiet bell tone. To imagine this process, picture two dark spheres suspended in a vast ocean of space-time. They do not glow, they do not shimmer, they make no sound in ordinary terms. And yet they are not silent. Their gravity creates a shifting pattern in the fabric around them, as if the sea itself is responding to their presence. With each orbit, they send faint ripples outward, tiny tremors that stretch and squeeze space across the cosmos. At first, when the black holes are far apart, their orbits are slow, calm, almost serene. They take millions or billions of years to drift closer, losing energy gradually. This energy loss does not happen through light or heat, it happens through gravitational waves. Every time they circle each other, they send out ripples that steal just a bit of energy from the orbit. As the orbit shrinks, the dance grows tighter. Their speed increases, the ripples grow larger. This is the great cosmic waltz of black holes, slow at first, then faster, then breathtakingly fast. Imagine them spiraling inward at half the speed of light, then 3/4, then almost fully chasing their own shadows. Time dilates, space twists, their horizons stretch toward each other, as if reaching out long before they touch. As they draw closer, the geometry of space-time becomes violently curved. The gravitational pull is no longer simply the sum of their masses. It becomes a dynamic field, constantly reshaped by their motion. The two horizons begin to deform. They bulge and elongate. They tug on each other's edges, distorting into shapes that look nothing like spheres. It is in this stage that gravitational waves become strongest. These waves do not propagate like light. They do not scatter off dust or gas. They do not blur or fade the way photons do. Instead, they pass through matter almost effortlessly, carrying a perfect imprint of the motion that created them. When LIGO detected the first such waves in 2015, the signal had traveled across 1 billion years. Yet it retained its shape so clearly that physicists could reconstruct the entire dance, two black holes spinning ever faster, ever closer, then merging into one. The final chirp in the signal, the rising frequency, the sudden cutoff, was the fingerprint of the collision. But what is the collision itself like? The moment the two horizons meet is not an impact in the traditional sense. There is no crash, no explosion of matter. Instead, the horizons merge like two soap bubbles touching. A new, larger horizon forms around them. The interior spacetime reorganizes. The singularities that once existed separately become a single, more massive one. But the merger is not gentle. There's a violent rearrangement of spacetime curvature. The new black hole is misshapen at first, wobbling, ringing, trembling. It oscillates, trying to reach stability. These oscillations emit gravitational waves in a pattern known as a ring-down. This ring-down is the quiet bell tone of the universe, a final fading note that tells us the black hole has settled into its new form. The energy released in this moment is staggering. In a fraction of a second, the merger can radiate more energy in gravitational waves than all the stars in the observable universe emit in light during the same instant. Yet this energy does not heat anything. It does not shine. It does not illuminate. It simply moves through space as pure curvature, ripples expanding outward forever. This process raises a profound point. Mergers are how black holes grow. Black holes do not reach their supermassive sizes through stellar collapse alone. They grow by feeding on gas, by absorbing stars, and by merging with other black holes. In the early universe, black hole mergers were common. Small black holes collided, forming larger ones. Those larger ones collided again. This chain of mergers may have helped build the titanic supermassive black holes we see today, some billions of times the mass of the Sun. Each merger leaves behind a slightly different black hole. The spin changes, the mass increases, the orientation of the horizon shifts, the surrounding space-time reconfigures itself. A merger is not just an event, it is an evolution. But the collision of black holes is not only about gravity and growth, it also reveals something deep about the nature of time itself. Near the merging horizons, time behaves strangely. Observers falling into each black hole would experience time differently from distant observers. The final moments of the merger unfold in ways that defy intuition. One observer might see the horizons merge seamlessly. Another might see the approach stretch into a near-eternal delay. The collision becomes a cauldron where all the oddities of relativity, time dilation, length contraction, gravitational redshift, frame dragging, are stirred together. This is why black hole mergers are so essential to our understanding of physics. They are natural laboratories for extreme space-time. They push our theories to their limits. They test the predictions of general relativity in realms far beyond any experiment we can create on Earth. And, remarkably, general relativity has passed those tests flawlessly. Every merger detected by LIGO and Virgo has matched the predictions nearly perfectly. Every chirp arrives in the exact frequency pattern the equations foresee. But the detection of mergers is not only about confirming existing physics, it also opens doors to new physics. Some theories predict additional kinds of gravitational waves, echoes, whispers, faint tones that could reveal quantum effects near the horizon. Others predict deviations in the ring-down signal that could hint at exotic objects like boson stars or modified gravity. For now, no anomalies have been found. But with every detection, our ability to probe these cosmic events improves. Black hole collisions may eventually help uncover quantum gravity, the missing bridge between general relativity and the quantum world. The collision itself, though invisible, affects the universe long after the waves pass. The new black hole recoils. If the merging black holes had unequal mass or spin, the resulting black hole can receive a kick, sending it drifting through space at hundreds or even thousands of kilometers per second. Some black holes may be kicked entirely out of their host galaxies. These wandering black holes, alone, dark, drifting through intergalactic space, are the quiet remnants of ancient cosmic collisions. And yet, despite their violence, these events do not threaten the universe in any destructive way. They are simply part of its evolution, a natural, quiet consequence of gravity working over immense timescales. What makes black hole mergers so hauntingly beautiful is that we can hear them, not with our ears, but with detectors sensitive to motions smaller than a proton's width. When a merger's gravitational waves arrive on Earth, they stretch and compress our planet ever so slightly. And in that stretching and compressing, we witness the heartbeat of the cosmos, two black holes circling, spiraling, and finally becoming one. The universe does not need light to tell its story. Sometimes it speaks in curvature, sometimes it speaks in motion, sometimes it speaks in waves. And as we drift deeper into this quiet exploration, one more question begins to rise gently from the horizon of understanding. If black holes merge, lose energy, and evolve, what happens to the information carried by everything that has ever fallen into them, and can that information ever escape? Part 13. Could a black hole ever erase information? Physics tells us that information cannot be destroyed, yet black holes seem to swallow it without return. This contradiction is the information paradox. Does the information escape through Hawking radiation? Is it stored on the horizon's surface? Is spacetime itself holographic? Black holes sit at the crossroads of our deepest scientific questions, holding secrets we are only beginning to unravel. To understand why this paradox matters, imagine following a single particle as it moves through space. Perhaps it is a photon emitted billions of years ago by a distant star. Perhaps it is an atom drifting quietly between galaxies. No matter what happens to it, collisions, interactions, transformations, the information describing its state must always remain present in the universe. It may spread out, it may be scrambled, it may become unimaginably complex, but it cannot vanish. This is one of the bedrock principles of physics. Yet, black holes challenge that principle. When something falls past the event horizon, it cannot return. It cannot send signals. It cannot leave behind a trace that escapes. Everything about it, its mass, charge, spin, affects the black hole, but all finer details disappear behind the horizon. According to classical general relativity, the black hole forgets everything except those three macroscopic properties. Two stars with different compositions would produce indistinguishable black holes once collapsed. This is the origin of the paradox. A universe that destroys information contradicts quantum mechanics. A universe that allows information to escape a black hole contradicts general relativity. These two great theories collide at the horizon, and neither emerges unscathed. Stephen Hawking initially believed that information is lost. He argued that Hawking radiation is perfectly thermal, featureless, structureless, containing no trace of the material that fell in. If a black hole evaporates entirely through this radiation, he reasoned, the information it swallowed disappears with it. But this conclusion shook the foundations of physics. It suggested that quantum mechanics would need to be rewritten. Other physicists refused to accept this. They argued that quantum mechanics must hold everywhere, even at the edge of a black hole. If information is preserved in ordinary processes, why should a black hole be different? Somewhere, somehow, the information must remain hidden or be released. To understand the debate, imagine dropping a book into a black hole. Every word, every letter, every atom in the book contains information, its arrangement, its motion, its internal structure. When the book falls past the horizon, that information seems lost. But quantum mechanics insists it must still exist in some form. Where is it? One possibility is that the information becomes encoded in the Hawking radiation. Instead of being perfectly random, perhaps the radiation carries subtle correlations, tiny patterns that encode the details of what fell in. If this is true, the radiation is not truly thermal. It only appears thermal at first glance. Over immense timescales, the information would leak back into the universe, scrambled but preserved. This idea leads to the Page curve, a prediction from quantum theory that describes how a black hole's entropy rises as it absorbs information, then falls as it evaporates. Recent calculations in quantum gravity match the Page curve, suggesting that information does indeed escape, but in a deeply scrambled form, almost impossible to reconstruct. Another idea is that the event horizon itself holds the information. Jacob Bekenstein showed that a black hole's entropy is proportional to the area of its horizon, not its volume. This suggests that the horizon acts like a giant storage surface, a cosmic ledger recording everything that has fallen inside. The information is not lost, it is smeared across the horizon in microscopic degrees of freedom. This concept led to the holographic principle, a profound idea that the information inside a region of space may be encoded on its boundary. In this view, the three-dimensional interior of a black hole could be fully described by two-dimensional data on the horizon's surface. The universe becomes holographic, its deepest truths stored not in volume, but on surfaces. But the paradox deepened with the discovery of firewalls. Some physicists suggested that if information is encoded in the Hawking radiation, then the horizon cannot be smooth. Instead, it must be a seething, violent place, a wall of high-energy radiation that destroys anything trying to cross. This contradicts general relativity, which predicts a smooth, uneventful passage for falling observers. To accept firewalls, we would need to abandon one of the foundational insights about black holes. So we face a trilemma. We cannot keep all three of the following ideas without contradiction. Information is preserved. An observer falling into a black hole experiences nothing unusual at the horizon. Quantum field theory works normally outside the horizon. One of these must give way. Recent developments in string theory, quantum gravity, and holography point toward a new idea. Information is stored in correlations between interior and exterior states, and the horizon remains smooth. In this view, the black hole's interior is not separate from its exterior. It is encoded in a non-local way. Space inside the horizon may not be a region in the classical sense, but a quantum construct emerging from entanglement. In this interpretation, the information paradox dissolves not because information escapes, but because the notion of inside and outside becomes far more subtle than we imagined. Some theorists even propose that black holes are fuzzballs, objects made entirely of strings or quantum states with no singular interior at all. In this model, the horizon is not empty. It is a tangle of quantum fields. Hawking radiation emerges naturally from this structure, carrying information with it. The black hole evaporates, but the information is never lost. It is woven into the fuzz. Others suggest that Einstein-Rosen bridges, wormholes, connect the interior to the outside world through quantum entanglement. This is the EPR conjecture. Entangled particles may be connected by geometry. If true, the black hole's interior could be linked to the Hawking radiation outside by a microscopic wormhole structure, allowing information to transfer without violating relativity. We do not yet know which picture is correct. What we do know is this: black holes do not casually defy the laws of physics. They test them, they sharpen them, they force us to confront the limits of our understanding. The information paradox is not merely a puzzle, it is a doorway into the next era of physics, an invitation to develop theories that unite gravity and quantum mechanics. And perhaps the most beautiful truth is this: the paradox exists because black holes sit where our two greatest frameworks, quantum theory and general relativity, overlap. They are the crucibles where old ideas melt and new ones take shape. Whether the information escapes, is stored, or transforms into a holographic imprint, the universe does not simply erase the story of what falls inside, it hides it, it encrypts it. It scatters it across spacetime in ways we are only beginning to perceive. And as we drift quietly toward the next chapter in this journey, one more gentle question emerges. If information is preserved and black holes evaporate, what remains at the very end? What is the final whisper of a black hole as it fades into nothing? Part 14. Do black holes really act as time machines? Near a black hole, time flows slower. Far from it, time flows faster. This gradient means that two observers can live through vastly different durations of existence depending on where they stand. While black holes cannot send you backward in time, they can stretch your future into someone else's past, creating a quiet imbalance that reveals just how flexible time truly is. To understand this imbalance, imagine time not as an arrow, rigid and uniform, but as a river whose speed changes depending on the shape of the land beneath it. In most places, far from massive objects, the river flows smoothly and consistently. Seconds pass with comforting regularity. But near extremely dense objects, like black holes, the river slows, it narrows, it thickens, it becomes harder to move through. General relativity explains this through the curvature of spacetime. Mass tells spacetime how to curve, and curved spacetime tells time how to flow. The deeper the gravitational, the slower time runs. In everyday life, we barely notice this effect. Time on Earth's surface runs a tiny bit slower than time at higher altitudes. A clock on a mountaintop ticks very slightly faster than one at sea level. But the difference is minuscule, so small that you need atomic clocks to measure it. Near a black hole, however, the effect becomes extraordinary. If you hovered safely outside the event horizon, held by powerful rockets or orbiting at incredible speeds, you would feel time move normally for you. Your heartbeat, your breath, your thoughts, all would follow their usual rhythm. But a distant observer watching you would see something very different. Your clock would appear to slow. Your motions would seem to stretch. As you approach the horizon, you would seem to freeze entirely. To you, nothing strange has happened. To a distant observer, you have nearly stopped. This divergence is not an illusion. It is the nature of time itself. Your personal experience remains unchanged because you ride the curve of spacetime. The distant observer, however, views the structure of time from a different part of the river, and their vantage point reveals a completely different flow. This is why black holes behave like one-way time machines. You can move forward in time relative to others much faster than they can relative to you. Suppose you orbit a black hole at a safe distance for a few hours. When you return, decades or centuries might have passed in the outside universe. Your personal timeline remains short, while others have experienced long stretches. You have traveled into their future, but they cannot travel into yours. This asymmetry does not allow you to revisit the past, but it does allow the future to arrive unevenly, as if time has become elastic, stretching, bending, and billowing like cloth in a silent cosmic wind. The deeper you fall toward the horizon, the greater this stretching becomes. Imagine dropping feet first toward a stellar mass black hole. If we momentarily ignore tidal forces, which would otherwise tear you apart, you would experience a smooth, uninterrupted fall. You would cross the event horizon in finite time. You would not notice anything particularly strange, but the outside universe would watch you slow endlessly, fading into darkness, never truly vanishing from their perspective. You live your future. The universe sees you stall in theirs. This is time dilation pushed to its extreme. But the strangeness deepens when you consider spinning black holes. Their rotation twists spacetime, dragging it along in a phenomenon called frame dragging. Inside the ergosphere, the region outside the event horizon, you cannot remain still. Time and space both swirl, forcing you into motion. In this region, the future pulls you forward like a current you cannot resist. A spinning black hole enhances the time-warping power of gravity. You orbit closer, you move faster, your clock slows more dramatically. And yet you remain in a stable path longer than you could around a non-spinning black hole. These stable orbits mean that one could, in theory, orbit a spinning black hole for hours while the universe outside ages dramatically. Movies like Interstellar captured this idea. though they exaggerated certain aspects for narrative effect. The underlying physics, time dilation from extremely curved spacetime, is real. But the question lingers: does this make black holes true time machines? The answer depends on how one defines a time machine. A black hole does not allow you to revisit events that have already happened. It does not let you travel to yesterday or undo choices. It does not let you loop back to the moment you left. Time inside a black hole always flows forward, always toward the singularity or whatever lies beneath the horizon. There is no going back. But it does allow differential aging, a quiet splitting of timelines. One observer's short journey becomes another's long wait. Time remains consistent locally, but inconsistent globally. This is the essence of gravitational time dilation. Time is not absolute. It is shaped by mass, motion, and geometry. This leads to a deeper truth. Black holes do not break time. They reveal what time really is. Time is not universal. It is not shared evenly. It is not a single rhythm beating in all corners of the cosmos. Instead, time is personal. It is local. It is tied to the path you follow through space-time. Black holes expose the flexibility we usually ignore. Their extreme curvature allows us to see the rules that govern time in everyday life, but are too subtle to notice. They magnify the quiet elasticity that permeates the universe. Now consider what happens after a black hole has aged for eons. As it slowly evaporates through Hawking radiation, the space-time around it becomes less curved. The time dilation weakens, the gradient softens. The immense difference between inner and outer clocks gradually fades. Over unimaginable timescales, the black hole's effect on time diminishes until it finally disappears. But the imprint of its presence, how it stretched time for billions of years, remains in the universe's history. Some theorists speculate that the internal structure of a spinning black hole might contain regions where space-time becomes so twisted that closed time-like curves, loops in time, could form. But these regions lie beyond the event horizon, where classical descriptions break down. Quantum gravity, which we have yet to fully understand, likely forbids these loops or alters them into something non-traversable. Nature seems careful. It allows time to stretch. It allows time to bend. It allows observers to experience vastly different durations. But it does not allow paradoxes. It does not allow violations of causality. Black holes are not shortcuts through time. They are amplifiers of time's geometry. Their greatest gift is not the ability to travel into the future that can be achieved with ordinary high-speed motion as well, but the clarity with which they reveal the universe's indifference to uniformity. Time does not care about fairness. It flows differently for each of us, shaped by where we are, how fast we move, and what we orbit. Black holes simply make this truth undeniable. And as we drift gently toward the next question waiting beyond this one, a quiet thought lingers in the back of the mind. If black holes can stretch time so dramatically, what becomes of the universe itself as it grows older? What role do these dark giants play in shaping the cosmos across the span of cosmic ages? Part 15. What do black holes teach us about the fate of the universe? In the far future, when stars fade and galaxies drift apart, black holes will remain. They will outlive starlight, outlive planets, outlive nearly everything. And as they slowly evaporate over trillions of years, they may be the last places where time continues to flow meaningfully. The universe's final chapters may be written in the dim glow of their slow dissolution. To contemplate the fate of the universe, we must first understand the role black holes play across cosmic time. They are not merely exotic objects scattered throughout the cosmos. They are milestones, markers of what the universe becomes as it ages. In their formation, we see gravity's triumph over matter. In their evolution, we see the whisper of quantum effects at the threshold of spacetime. And in their final evaporation, we glimpse the last flickers of activity in a future where almost everything else has gone quiet. Imagine the universe trillions of years from now. The youngest stars have long since stopped forming. Galaxies have grown sparse and faint. The cosmic background radiation, the afterglow of the Big Bang, has faded into near silence. Even the light we see today from distant galaxies will be stretched beyond recognition by the expansion of space. In this far future cosmos, the objects that once filled the night sky are gone. Red dwarfs, the longest-lived stars, have burned through their fuel. White dwarfs have cooled into black lightless spheres. Neutron stars remain as cold, dense fossils. Matter has fallen quiet. Yet in this darkening universe, black holes endure. They sit in the empty vastness like the last embers of a fire, massive, silent, ancient beyond comprehension. Their gravitational fields persist even when the universe has little left to shape. And in that persistence, they become timekeepers of the deep future. Black holes reveal a profound truth about cosmic fate. Gravity is slow to fade, even when everything else succumbs to coldness. But black holes do not last forever. Hawking radiation, one of the most astonishing predictions in physics, ensures that black holes radiate energy, slowly losing mass in the process. For a supermassive black hole, this evaporation takes far longer than the age of the universe, so far. A black hole with the mass of the Sun would take about 1,067 years to evaporate. A supermassive black hole at a galactic center might take 10 to 100 years or more. These numbers are so large they barely feel real. They are timescales on which galaxies themselves seem like brief sparks. But black holes are patient. They persist through eras of cosmic stillness. As the universe expands, distance itself grows. Galaxies drift apart faster than light can cross the space between them. Each galaxy, or what remains of it, becomes a lonely island, isolated from all others. Eventually, even the memory of structure fades. Gravity weakens on large scales. Expansion wins, but not locally. Where matter remains bound, around black holes, gravity still shapes time. In this far future era, black holes become the last active astrophysical objects. When the universe is too cold for stars to shine, too stretched for new structures to form, black holes remain places where processes still occur. Their Hawking radiation continues, faint but real. Time still flows around them because the curvature they impose on spacetime has not yet dissolved. They are the last engines. But what did they reveal about the universe's destiny? One lesson is that the universe tends toward simplicity. In its youth, it was chaotic, flooded with radiation, turbulence, collisions. As it aged, structure emerged, stars, galaxies, clusters. As it ages further, structure dissolves, complexity fades. What remains are the simplest objects allowed by physics, black holes, and eventually, not even those. Another lesson is that quantum mechanics and gravity shape the universe's end as surely as they shape its beginning. The Big Bang was an interplay of quantum fields and space-time expansion. The final evaporation of black holes will be the same. Tiny fluctuations at the edge of an event horizon, virtual particles flickering in and out, will dictate the last release of energy. When the final black hole evaporates, the universe enters what physicists call the dark era, an era with no stars, no galaxies, no black holes, no light. Only diffuse particles, drifting across an ever-expanding emptiness, and yet, even here, black holes leave their mark. Their evaporation injects the tiniest bit of structure into an otherwise silent cosmos. They prolong activity. They sustain a trace of energy far beyond the lifetimes of stars. In this way, black holes teach us something subtle. The universe does not end abruptly. It fades softly, quietly, like a breath exhaled over unimaginable spans of time. But there's a deeper lesson here, one more profound than lifespan or thermal radiation. Black holes reveal that time itself will change as the universe ages. As expansion accelerates, regions of space drift beyond each other's horizons. Events in distant galaxies become inaccessible. Even the past becomes unknowable because its light never arrives. Time becomes fragmented. Across the universe, different regions experiencing their own isolated futures. Black holes emphasize this separation. Their deep gravitational wells slow time dramatically. Their evaporation occurs on timescales meaningless to stars or planets. Each black hole becomes its own timeline, ticking according to its mass and curvature. In the universe's final ages, when only black holes remain, These isolated timelines dominate. Each black hole lives out its own extended future, radiating softly into the void. When the last one evaporates, the universe becomes a place where time flows uniformly again, but with nothing left to experience it. Black holes teach us that the future of the universe is not simply darkness, it's silence. A silence shaped by the interplay of gravity, quantum fields, and expansion. A silence defined by the last remnants of curvature slowly smoothing out. And yet, paradoxically, black holes also symbolize resilience. They are the final survivors of cosmic evolution. They carry the last traces of structure. They remain active long after stars have died. Their gradual dissolving, photon by photon, may represent the universe releasing its final stored energy back into the emptiness from which it emerged. Black holes teach us that the universe's fate is not catastrophic, but gentle. Not a dramatic collapse, but an endless drifting. Not a violent end, but a slow unwinding. And there is something almost comforting in the thought that the universe ends not with destruction, but with stillness. When we observe black holes today, when we watch stars swirl around them or see shadows captured by telescopes, we are not just witnessing extreme physics. We are watching the universe rehearse its final act, an act that will unfold long after all familiar structures have faded. Black holes show us the trajectory of cosmic time. They reveal how the universe ages. They hint at how it will end, not in fire, not in collapse, but in the quiet release of its last stored complexity. And as we gently close this final chapter of the body, one more truth settles softly into place. To understand black holes is to understand the universe's beginning, its middle, and its distant twilight end. They are the bookends of cosmic history, its first mysteries and its final echoes.